in this chapter we have is the Oersted's experiment. Oersted. Oersted's experiment. Okay.
Yeah.
This is the experiment that led to the discovery of the magnetic effect of electric current.
Okay.
Okay.
Yeah.
So in this experiment we have a magnetic needle. So this is something it looks like. This is a magnetic needle. It is a stand. Okay. Now it always points in the north-south direction. Correct?
Yeah.
So this needle can move freely
Yes.
and it always points in the north-south direction. Now what he did was, this Oersted, he took a circuit, okay, which consists of a battery, a key, right, and then a battery, and you can also put in an LED here, or you may not. But okay, this is the circuit. This is still the circuit.
Yeah.
This is a Biot battery. So when this circuit is complete, a current will flow in this direction. Correct?
Yes.
Now, after this, what he did, he brought this needle very close to this circuit.
Okay.
All right.
Yeah.
So when he did that, he found that this got deflected.
Okay.
All right.
Yeah.
And then further, what he did was he changed the polarity of the battery. So in this case, he changed it like this. Then the current would flow like this.
Yeah.
And now when you brought that again close to this circuit, the needle got deflected
In the
again,
opposite
but in
direction.
opposite direction. Yeah, correct?
Yeah.
So this led to one thing, that the current, because since this is a magnetic needle, right?
Yes.
This can only be deflected by a magnet, isn't it?
Yes.
This magnetic needle can only be deflected by, because it's made of a magnet.
Yeah.
But when he saw that it's being deflected by this circuit when we brought in close it, so it led to the conclusion that this circuit has some magnetic field around it.
Okay.
This wire develops a magnetic field around it. Only then this magnetic needle can be deflected, because it can only be deflected by some other magnet, right?
Yeah.
So this is the discovery of magnetic effect of. You can also do this at your home. So if you have a battery which is enough voltage, not 1.5 volt battery, you cannot do that because it's very small voltage, right?
Yeah.
And let's say if it is a 12 volt battery or something like that. So if you brought in close iron piece to it, okay?
Yeah.
So for example, a nail cutter or something, then this wire will attract it, you will see. Because this has now become a magnet, The wire itself has become a magnet.
Yes.
Okay. So by this experiment, there is one thing that we have got, that we should write it. So current carrying wire behaves as a, I'm not going out of frame, or do tell me if I am. So current carrying wire behaves as a magnet.
Yeah.
Okay.
Yeah.
Now let us just start. Biot Savart law. So
Okay.
these were the two scientists, Biot Savart law. So this law is used to find the magnetic field. Suppose we have a wire.
Yeah.
Okay.
Yeah.
This is a wire carrying a current I. Now, from the previous discussions, we know that this wire, when carrying current, will have a magnetic field around it. Okay.
Yeah.
And there is also a method to know the direction of that magnetic field. Suppose the current is in this direction, right?
Yes.
Okay.
Yeah.
So magnetic field can be either in this way or in this way.
Yeah.
So how will you find the direction? The simplest way is to put the thumb along the line of the current,
Okay.
okay?
Yeah.
And the direction in which the finger curls will be the direction of magnetic field.
Okay.
But use the right hand only. So right hand,
Thumb rule.
not thumb rule.
Okay. No. Then what is it?
Hello?
Yes.
So this is the right hand.
But, but you just said it's not the right hand thumb rule, right? Awkward.
I'm sorry, someone interrupted midway.
But you said it wasn't right hand thumb rule.
No, it's right hand only. You were saying something else. I think you were saying the palm rule. There is right hand palm rule also.
No, I said right at thumb rule. I'm pretty much sure I
There
said
is
that.
right hand palm rule and there is Fleming's right hand rule. There are
Oh, okay.
three right hand rules. So this is used to find the direction of magnetic field. Now we have a current carrying wire, right? We want to find at some distance from it, at point P, we want to find the magnetic field due to a small current carrying element dl. Okay,
Okay.
what is dl? If L is the length of the
Small.
whole wire,
DL is the
then the
small.
small length is dl. This is the small length. Okay,
Yeah.
so due to this length, we want to find the magnetic field at some point P, anywhere close to this wire, right? So first of all, we join this. Okay,
Okay.
and now let us say this vector is r vector from dl length up to P. All right,
Yeah.
and further the angle between this line and this wire is theta.
Okay.
Correct.
Yeah.
Now this dl length will produce a small field dB. Okay,
Okay.
it is equivalent to electric field. See, E denotes electric field and B denotes magnetic field. All right.
Yeah.
So this dl length will generate a small dB magnetic field. Correct.
Yeah.
And the formula for that is dB is equal to mu naught. Well, let's first write the magnitude only. Mu naught upon 4 pi I dl sine theta divided by r square.
Okay.
Correct.
Yeah.
This is the formula. So as you can see, this dB is proportional to I. That is, more is the current flowing through the wire, more is the magnetic field. This dB is proportional to sine theta as well. This dB is inversely proportional to 1 by r square. Correct?
Yeah.
And this is also proportional to dl. Okay.
Yeah.
So first you should write this formula.
Okay.
Have you written this?
No, if you could just move. Oh, wait, actually, no, I got it.
Tell me when you are done with this. Meeting will end in 10 minutes. Uh, use the pro version.
I'll have to pay for it.
I'm never gonna pay.
Yeah, I wrote it.
Rodent.
Yeah.
I also do something for the lighting. It's not proper, I think, right?
Looks fine.
It's fine. Okay. So this is the formula. Now, again, since this dB is a vector quantity, in fact, B is a vector quantity,
Okay.
similar to E, as E is also a vector, because this is a field, right? Field should be a vector.
Yeah.
Now we want to know the direction of this field due to this wire carrying current I. There will be a field at this point given by this. But what will be the direction of that? Okay.
Yeah.
So for that, you also write the vector formula of this dB vector. And that is mu naught upon 4 pi I dl cross r, okay,
Yes.
upon r cube. All right.
Yeah.
This is the vector formula. Now, in this formula, you can see the direction is given by dl cross r.
Yeah.
dl cross r means see, this dl is in the direction as that of I. Remember, okay?
Yeah.
This dl is in the direction of current. And this r is from, let's say this point is O. So r is from O to P, correct?
Yeah.
So dl cross r, how would you find dl cross r? See,
Mm,
let me tell you. How do you find the cross product of two vectors? Suppose there is this vector A, there is this vector B.
yes.
How will you find A cross B, or let's say B cross A, B cross A? You will put palm like this and move along A, and then the thumb direction will be the direction
Direction
of
of.
cross product.
Yeah.
So B to A, right, like this.
Yes.
This is right hand palm rule, okay?
Yeah. Okay.
From B to A you move, and then this. Now here also, if you zoom it, can I erase this?
Yeah.
It can end at any time.
There's
So
still
before
5 minutes.
I need to finish.
Okay.
So this is DL, let's say.
Yeah.
All right.
Yes.
This is R.
Oh.
So DL cross R will be inside the board. Okay.
Yes. Yeah.
You put it like this and then this.
Yeah. It
So
will
this
be
thumb will go
inverse.
inside.
Yeah.
So that's why I put in a cross here. So cross means inwards. And this dot means
Outwards.
outward.
Okay.
Okay.
Yeah.
So the direction will be inside, okay, inside the board
Yeah.
in this case. Okay, so what is this K? Let's say, hmm, I should erase this as well. So there is the thing called mu naught upon 4 pi, right? This is a constant.
Yeah.
Let's say this is some K, and its value is 10 to the power minus 7 Weber per ampere per meter. This is the SI unit.
Okay.
All right.
Yeah.
It is also called as Tesla meter per ampere.
Oh,
Okay.
okay. Yeah.
So you should write this as well.
Tesla
Now from here, yeah,
meter
Tesla meter
or
per
ampere.
ampere.
Okay.
Here. And from here, this mu naught would be what? 4 pi into 10 to the power minus 7, isn't it?
Yes.
So either you remember this mu naught upon 4 pi is equal to 4 times this, or you remember this. Anyone you can remember. It's the same thing.
Oh, okay.
So that's it for today.